Prima, dopo o durante? Ottimo. Alla fine va lo stream? Grande, grazie. Quindi è un problema se lo facciamo in inglese.
Non so, ora chiediamo. Ho scritto c'è il pulsante Go Live in alto a destra, però dici che lo vedi? Ah, no, si vede.
Ma dici di...
Cosa?
Dici qua su YouTube?
Sì, tu stai vedendo, no?
Sì, adesso
Sì, cazzo.
Incredibile. Ma ci
Me
siamo
la attacco
dentro.
sulla macchina così dopo quelli che programmano in scala me la rigano.
Ah, ok, scusa.
Ecco qua che dopo.
Andiamo?
Ottimo.
Vai, Marco. Sì. Sono solo? Ah no, l'avevamo sempre fatta in due.
Io faccio l'albero.
Ok. Ma c'è qualcuno che sapere l'inglese?
No, devo parlare in inglese.
Dobbiamo parlare in inglese? Ok. Hi all, this is Python Milano Meetup. Here is Cesare and Marco. Okay, who we are? So we are a community open to developers and hobbyists having fun with Python. Welcome to everybody. And what do we do? So we do meetups like this one. We do Pi Birra, which means Pi beer. So basically hanging around in a pub, speaking about Python and information technology in general. And we also do a podcast in Italian, it's not in English, which is called Python, Intervista Pythonista. Okay. So here is our links for the community. The main links is milano.python.it. And sorry? Oh, yeah, the second one is broken, actually. we open an issue in GitHub to fix it. If anybody can help us to fix it, it's welcome. We accept any merge request, etc., etc. And all the other links are contained into milano.python.it. Okay, thank you for the venue, to Fabio and Mirta. It's the third time in a row that you are hosting us. If you want to say something about Mirta, what you do, etc., etc.
Thank you. Thank you, Cesare. Yeah, thanks everyone for coming. We're really happy always to host you. Just very briefly, what is Mirta? We are a startup. We are a marketplace in the fashion industry. We also have a big tech team. We're working on solving some problems in the B2B space, selling pretty much made in Italy products around the world. And so we use Python, we use many technologies on AWS. So we are really happy to host this kind of meetups where everyone can learn and share and do networking. So yeah, thanks.
Thank you, Fabio. And we also want to thank Python Italia. Python Italia is an organization which organizes every year the Python Italia in Florence, and also provided the cam and the microphones, etc., etc. So thank you, Python Italia. And we want to thank also Division Lab, which is the people who gave the money to Python Italia to buy all the
The camera
all the
and
stuff.
streaming, the equipment is provided by
Yeah,
Digital Lab, which is
and also the OBS studio setup that I will never do it without the help of the CTO of Division Lab.
maybe we can explain because he's not here because he's sick. But Division Lab is an Italian startup that makes data visualization tools. So check it out if you want to know more.
Okay, and today we have two speakers. One is Luca Soato, and the other one is Luca Grazioli. And okay, the stage is yours.
Sorry. After the event, we will go to a dinner to take a pizza if you want to join. There is no reservation, so we'll try to find a table. Usually we make it. The pizza is not offered by any of the sponsors, so you have to pay it. But we would be glad if you want to join, and that's actually the best part of the event. And now we can start. Who is first, Luca?
We are both Luca, but
No, Luca, he.
the first one in time.
All right.
So, thanks everyone for the warm welcome. Okay, so let's start. We're all here today to talk about data pipelines, specifically with these three technologies that are Kubernetes, Airflow, and Spark. And we see how to use them together and how to integrate them together to build scalable data pipelines. So, just a small round of presentations. I am Luca Soato. I work in the data engineering team in Card.ai. And here with me, there is Luca Grazioli, that is our ML solution architect. And I'll be very brief to describe who we are and what we do, because we are in Card.ai, and it is a company that is revolutionizing the capital management in the digital economy. And this presentation that we are doing and this project that we are doing is basically the answer for a long-term data engineering strategy that we have developed for three main objectives. So the first one was to ingest huge quantities of data in a reliable and efficient way. The second one is that we had to adapt to the market quickly, so that we needed to have a fast time to market for our data pipelines. The third one is that we want to avoid to be locked in some sort of vendor. So we didn't want to get some really platform that is already made. So we wanted to focus on open source projects so that we can know from the very core of these products how we can use them and when we can integrate them together. And so that we can, of course, there are a few exceptions for some services that are now consolidated in the industry. But let's move on to have a brief summary of what we are going to do. So we're going to have a brief introduction on the architecture that we are following. So from just a brief historical chapters about what is a data warehouse and data lake, and the final architecture that is what we have developed in here in Card.ai, that is the lakehouse architecture. Then we're going to see these three technologies of Airflow, Spark, and Kubernetes alone, so that we can see what they are and why did we select exactly them. And then we're going on with seeing the integrations. So specifically, we're going to see first how to integrate Spark with Airflow. So we're going to see the previous attempt of integrating these technologies together, and we're going to see the task with Spark operator that we have developed internally here in Card.ai. Then we're going to see how to debug and configure these tasks with Sparks. So that basically this is something that usually it's not that easy to do, and how we have evolved and developed the developer experience around that. Then we're following the integration of Spark with Kubernetes. So how in Spark we can use pod affinities to achieve the desired results, so to minimize costs and to enhance the performance of our Spark jobs. Then how to scale dynamically the Spark executors. That is something that we wanted to achieve in case, usually you do it when you have some kind of, we have to do some workflows that are not, that you have to adapt to the workflows and to the size of data that might vary during the time. And then we're going to see the chapter of how the Kubernetes autoscaler works with Luca Grazioli, and that has also been a committer of that project some time ago. Absolutely. And then we're going to see how to how the Spark concatenates Kubernetes operator, and how it basically it is almost the same level of the yarn from the yarn that is basically the other option on the market to have Spark clusters, so that we're going to see some benchmarks against that, and then we're going to compare it to other kind of solution that is basically Cloudera and the EMR. To complete this presentation, we're going to see also the integration between Airflow and K8s. So the difference between the Celery and the Kubernetes executor for Airflow. And then we're going to see how task affinities, pains, and tolerations that are Kubernetes concept can help us when developing Airflow tasks. And how we integrate, we just described briefly how we integrate the Vault Secret backend. On another note, we can also see together, if we're going to have some time, also the next steps. So about some topics on this field that are pause pods, the optimal sizing of tasks depending on the node size, Spark-based storage servers, centralized monitoring, and some other things in the appendix. But just if we have time, or we can also do other presentations for that. So this is just what we're going into. So let's go on with the introduction. So just a quote from Bruce Lee. So adapt what is useful and reject what is useless, and add what is specifically your own. So let's go on describing the different architectures that we can have on the data engineering field. So basically, the data warehouse architecture is something that has begun that was basically invented during the 80s, and then it has became mostly established in the business, in the industry across the 2000s. And basically, it is a unified storage from multiple sources for structured data. So it's helping your company in your data standardizations. So basically, it is enhancing the data-driven decision of a company. So basically, you are trying to centralize and to create a central analytic database in which you can basically centralize the knowledge of your company and start to building reports, business insight, business intelligence tools. You can attach into that. So this is the first kind of architecture of this type. But there are, but not all that shines is gold, because of course, but you need gold to, of course, to pay data warehouses, because they are extremely expensive. Because in this kind of data warehouses, the storage is coupled with the computation many times. So, for example, in Oracle data warehouses, in case you need more storage, you also you need to add more nodes, and this can be somehow expensive on top of that. So and another issue that they are mostly inflexible. So whenever you want to add something that has a schema that might vary, the concept of schema evolutions are really slow to adapt, and all the data warehouses. So it's very hard to feed data science analytics projects on top of data warehouses. And that's why the Data Lake were born. So in Data Lake, you can just dump large amount of structured and unstructured data. It helps you creating your first data science project. So the advantages of that is that it is cheap and flexible. So for example, you can have an object storage or also block storage like HDFS, or in object storage you can have, for example, S3. If you are using AWS, you can dump a lot of data on that, but you have other issues because the problems are with data quality. So you don't know, for example, the schema of your data. and you don't know, for example, how to evolve that and to adapt on that. And this creates a lot of problems when you have to maintain the knowledge base, basically, all the data of your company. So it is a bit complicated as for the lack of data integrity. That's why the data lakehouse architecture was born. Basically, on top of this, you can have very cheap storage. It uses most of data lakehouse architectures that I've seen can use both block storage or object storage in implementations. Basically, it's always on top of some sort of services like S3 or, for example, AWS or HDFS in case of you have an on-premise cluster. But you can have, for example, when using some format like the Delta format, you can have also the ACID compliancy. So you have the data integrity on top of that. That is something very useful to have when you have to scale a lot. And you can build on top of that both data science and business intelligence projects. So this is the main advantage on why people are diving in the lakehouse architecture. I'm not going to describe it too deeply because, of course, this is not a meeting about lakehouse architecture, but I just wanted to mention so that we know why are we starting here and where are we going. Among the things that must be considered before implementing a lakehouse architecture is the fact that, of course, it relies on some sort of object storage or block storage to implement it, and this makes it somehow. Sometimes network can be the bottleneck when, for example, using with the object storage, and these are all things to consider before diving into this architecture. And that's it. So let's go on the technologies. So that's a small quote by Steve Jobs, technology, but no worries, we can go on. I don't want to bore you too much. Okay, so basically, let's go on and describe why did we choose these three technologies. So Apache Spark is an open source processing engine that can handle large amounts of data quickly and efficiently. But most of all, Apache Spark has become the standard de facto in the data engineering industry for processing huge amounts of data. It offers reliability. It lets you, I would say, compute huge amounts of data across several machines. And this is the advantage because it hides the complexity of all the networking, of all the problems that you could have when dealing with huge, with this kind of cluster setups. And it lets you work with, for example, with a SQL interface. So it really makes hard things simple. So this is why we went on and we decided to use Apache Spark. Then another tool is Apache Airflow. So as you could see, both in these and these are Apache tools. So this means that they are fully open source. So they have a huge community working on them. And the Apache Airflow specifically is a platform for programmatically authoring and scheduling and monitoring workflows. So in Apache Airflow, you can describe the work that you want to do as DAGs, directed acyclic graphs, in which the nodes of this DAG are basically tasks. So basically, you can have Python tasks, you can use operators on top of that, and you can use a different kind of task, for example, sensor, if you need to wait for a specific event to happen. So we went with the decision to use Apache Airflow because it's a wonderful product. It can scale us really well. Another advantage is the fact that it is written with Python. It makes it so easily to, for example, to change it, to adapt it, to modify it to your cases. So this is really it's really cool to work with it. So that's why we went for it. So these are the services, but we needed something at the core of our services to host these kind of services and to host them, to be the backbone of our and the foundation of everything. And we decided to go on with Kubernetes. Kubernetes is basically the result of 15 years of experience that Google has had, basically in automating the deployment and scaling and management of containerized application. So here we have the concept of containers when we have to use Kubernetes. So basically, if you're not familiar with containers, you can just think of them about some sort of recipe of basically in which you describe how to build a machine from the very beginning to all the binaries that you need and the libraries that you need for your workflows. And that's it. Why we decided to have Kubernetes as well as the foundation for our jobs. So let's go on with the integration. And the only way to make sense out of change is to plunge into it, move with it, and join the dance. Because if you're not ready, and if you're not quick to adapt the changes in the market, the problem is that your business might just crash. So that's why. So let's move on with Spark and Airflow. So let's see how we can integrate Spark and Airflow together. And so let's see the difference of our attempt and the one that were previous of ours. So before, basically, there are these concepts. Let's just check this concept. So I have this concept of the Spark driver, and the Spark executors. So when we have a Spark cluster, a cluster of machines that have to do our processes, we have these two kind of nodes. The Spark driver is unique because it tells you all the information about Spark, about the Spark application. It is responding to user program or input. So here is what you put your code. Yeah, whether it is SQL, whether it is a Python program in case of PySpark, it can be Scala, whatever. But this is what the core of your business logic is. And the thing that Spark driver does is to schedule the work across all the executors. So whenever you need, for example, to map, reduce, to do any kind of operation on a scale, basically the Spark driver maps it and wraps it and sends it to the executors. And the executors do the dirty job of doing all the stuff. So they execute the code assigned by the driver, and then they report back the state to the driver itself. This is why we have these two concepts. And the question is, so when we are using Airflow and the Airflow task, where should we put the Spark driver? Because one way that was already attempted to integrate Spark and Airflow was the cluster mode. So basically, you say you have an Airflow task. The Airflow task just says, okay, this is the Spark program that I have. These are the parameters that I want to run this Spark program with. And let's just send it to a Spark cluster, and that's it. But we didn't want to go with that because you're missing a lot of integration that you could have by having the Spark client directly into the task itself. Because if the Spark driver is the task itself, basically the task has access to all the Spark API. And on the other side, the Spark APIs has access to all the parameters that these tasks are sending each other. They are mentioned later as XCOM values, but these are the way that basically these Airflow tasks are exchanging the value together. These values are usually, they should stay in a database. So these are not like gigabyte-sized values. But for example, so if you want to transfer or to have to share between tasks, for example, a file that is gigabytes, you don't send it through these XCOM values, but you save it to a CSV or Parquet files. Sorry, I said something really bad for data engineer. And then you just mention the path and you share it between these tasks. So just to clarify the difference between the previous attempts of integrating these two technologies, basically on the cluster mode, you have to launch 3 pods, excepting the Spark executors, because you need a pod to launch the Spark application. Then there is the Spark driver, and then you need to have like an Airflow sensor that waits for the Spark application to be over. While in this, in our case, you just have one pod that basically knows when it starts and when it finishes, so you don't need to launch it or to wait it to end. So, and it is the Spark driver itself. So this is, but we didn't do it just to reduce the number of pods, of course. Of course, we also have a small drawback. So you don't, the smaller container image medal goes to the other attempt because, of course, you have different containers so that the image can be smaller. But you can call the Spark API from the task itself, and Spark has access to the XCOM values. That gives a lot of potential and eases the development a lot. On the other side, also, Spark is scheduler agnostic. So you are decoupling the program from the scheduler itself. That in some cases, it might be a wanted characteristic, but not in ours. So that's cool. Moving on, okay, these are some of configuration, for example, that I've just mentioned. So in case someone wants to reproduce our result, is that, for example, you have to take care of setting up the Kubernetes cluster as the master of a Spark cluster. Then the deploy mode must be set as a client. Another thing that, for example, you need to tell those Spark executors where the driver is, because they don't know it by themselves. So one way to do that is to have to give them the pod name and the pod IP address. But this can be mounted, since we are on Kubernetes. Okay, I'm the Spark Airflow part, but let's have a bit on the Kubernetes, because you can mount these kind of values as environment variables in the pod specification of the Spark driver. So this is something very useful when you have to deal with this kind of configuration. And then you can also select the pod template file of the Spark executors. So I mean, if you want to add any spicy dependency or anything that, or you want to change Spark in some sort of way or doing anything, you have the full control of what's happening. This is also some motivation that led us not to go on some vendor solution, but and to develop our own. So how do we design the development experience around Airflow and Spark? So we created this task with Spark operator that basically is just some sort of Airflow operator that you can put on top of the tasks. And you can look in this example how easy it is to just create a task with Spark. So basically, you can just create you can just put this decorator on top of this function. And for example, if you want to count how many lines are there in a directory in S3 full of CSV, you can just do it like that. I know that actually the protocol is not S3, it's S3A, but now in the latest changes, they made it so that you can work as with S3. So please forgive me for this shame, but that's it. And the process that we had to follow basically to create and to extend this operator just for reproducibility motivations. Basically, we just extended the Python operator of Airflow. Basically, we override the execute callable function so that we added our custom logic to get the Spark session here, and we feed it as an argument of the Python callable. So, and then we extended this just to do some magic with the decorators, and we included in the task decorator factory of Airflow. So through these processes that you can then find documentation, we should open source part of that so that at least there is easier things to do. So please ask us if you're interested. And then we achieved this task with Spark decorator. Then debugging, another thing that, okay, these are some difference between statically typed languages and dynamically typed languages. So why are you laughing? Is that because maybe I've done some typo or some something in the okay, maybe I wrote something wrong from the grammatic point of view, but sorry in that case. So basically, how to debug Spark with tasks? Basically, some of the usually developers that are developing in languages like Scala, Java, like that, they are basically swimming through debuggers. When they go to sleep, they keep debugging themselves because there are not as many interactive tools as in dynamic languages like Python or JavaScript to interact with their programs. So it's very hard. It's different when developing in dynamic languages and statically typed languages. Sorry if it is some type of like this. But we still wanted to have a debugger so that we could debug Spark tasks, because it really eases the development of them. And I'm just showing you the example of the what is it called? Visual Studio Code example, because that was the easier one. So just to, if you want to enable the remote debugging on Visual Studio Code, you can just do it with a decorator that we have developed, and you can put it on top of a function, of a task that you have you want to have. So yes, we love decorators. It's true. But and you can just then start put breakpoints on your function, and it will work really smoothly. And you can see here how we've developed these remote debuggers. So basically, we have the decorator, we have installing debug py, and then we are waiting for the client to connect there. Some of you may ask, but what if someone wants to use it instead of Visual Studio Code, wants to use PyCharm? This is a bit harder, because with PyCharm, you're not doing a port forward to the pod. You have to create a reverse proxy from the pod to your PyCharm environment, and this makes things a bit harder. So if anyone from the PyCharm team listen to us, please change this stuff. But thanks to the awesome work of Sebastian, a colleague of ours, we were able also to achieve that. And basically, the only thing that we had to do is to use also telepresence. That is another really useful tool when you develop on the solution on Kubernetes, because basically we created this intercept that works is basically a sort of a reverse proxy for Kubernetes pods. But this is another story. So let's go on the configuration of Spark, because it is very easy also to configure Spark like that. Because how many of you have ever used the Spark or have experienced also in the deployment of Spark and so on? Okay. How many of you consider Spark easily configurable or easily deployable? Okay. Okay, but I mean, we use it as well. It's cool to have Databricks because it eases all that part. But if you have to do everything from scratch to deploy it and to configure it, is a pain in the. We understand. But so we created this some sort. Okay, there are three kinds of configuration basically that you can have. At least I've grouped it like that. You can have the configuration on the Spark Builder. So basically, if you want to add some dependencies, like to connect it to S3, to Delta, or to use PyArrow, yes, they're basically almost direct when you use it on Databricks. Yeah, I know it. I hope you enjoy the USPA as the icon. Then you have configuration that have to do with the Spark driver. So how much CPU should the Spark driver have? So how much memory should the Spark driver have? The image from the containerization point of view. And then there are the Spark executor configs. How many of them should there be? Or should we enable the executor auto-scaling, or the CPU, or the memory, or everything? So, and you need this configuration to be known at different times of the process. Because, for example, the first that you need is the Spark driver config, because before spawning the pod, the Spark driver, that is the only pod that of the Airflow task that gets spawned, you need to know them beforehand. So this logic must be considered during the DAG parse, when you parse your DAG, that is the directed acyclic graph. While after you need to do you need the Spark build configuration because you need to build the Spark session, and also on that you need the Spark executor configuration. So you need to know this kind of information. And we have built some configuration classes on top of enabled tuples. Now it's just a reduced version. That's just to show you the process that we've used, so that we could have basically some sort of some of these parameters already there available, and to use them on top of Airflow tasks has been extremely easy because unless some slide disappear. But this, okay, a slide decided maybe it will come later, or there's been disappeared. But there was a beautiful example because you can basically inject this Spark driver configuration and builder configuration on top of the task with Spark. So if you put them as an argument of task with Spark, it will just retrieve this configuration and it will use it at runtime when the task will run. So that is very useful to use this kind to map the configuration like this. Okay, I'm sorry for that slide. Okay, that's it. Then we're gonna see how to integrate Kubernetes with Spark and the advantages of running Spark on Kubernetes. Because one of the main advantages is that some cool thing that you can do. For example, if you have a Kubernetes cluster and this cluster spawn different availability zone in AWS, for example, but I think that for other kind of vendors is very similar. One issue that you could have is, for example, that you could have these Spark executors distributed across different availability zone. This is not something that you like to have when dealing with these tasks because they are limited in time. So it wouldn't make sense to make them, how to say, redundant and highly available across availability zones in case of floods or any case of like this, because their lifetime is very limited. So you can use the pod affinities so to make sure that these Spark executors are located all in the same availability zone. This is something that we have enforced also to avoid cross availability zone communication costs, because as you may know, if you use AWS, is that the communication between availability zones can cost a lot of money. Also, you can see here just a small piece of our template, so that something that we have required is that these Spark executors are all located together, while something that we have selected as preferred is that the executor itself is close to the driver itself is close to the set of executors. So that is at least we have defined them in a different way. Another beautiful thing of having Spark on Kubernetes is the fact that you can have a dynamic allocation of Spark executors. So let's say that you have a daily job that needs to be executed every day, for example, counting CSV or whatever. And but there is some sort of this task becomes unpredictable from the workload perspective. This can become a problem because you don't know how to exactly size the workload and the Spark cluster. But with the Spark dynamic allocation, basically you can set it up so that you can have as many Spark executor as Spark needs. So basically, when it detects that there are jobs pending inside the Spark cluster, it just spawns other Spark executors. So basically, that this kind of task can scale a bit better. Of course, there are some limits on that because it's not true that all the jobs in Spark scale well with the number of executors. In some cases, for example, when you have to do the delta optimization, you prefer to have a bigger but lower number of executors, for example. But this, you have to know it when you deal with that. One thing is that, okay, you can see here an example of our Spark builder configuration and Spark executor configuration, because, for example, we selected that delta is true and pyr is true, for example, for the Spark builder configuration, and we set up a executor to scaling. And we can do this on task basis. So if the different tasks need different kind of setup, you can do them and just inject them in the task with Spark, the creator, and it works seamlessly. I think now it's time to discuss also the auto-scaling from the Kubernetes perspective. So
thank you. Hi everyone, I didn't have the chance to introduce myself. I'm Luca, a ML solution architect for the data science team in Cardo, or in other words, the person that usually data scientists blame when something goes wrong, and most of the time they are right. So, but in other words, I also take care of the infrastructure that it's underlying everything that Luca already introduced us. And I wanted to give you a brief introduction on how we can achieve automatic scaling in Kubernetes using all the components that are deployed and made available by the Kubernetes community and also by the cloud providers. So I will take a step back on how Kubernetes works, because maybe not every one of you knows how Kubernetes works, and which is the nomenclature and namespacing of everything that we can use, which are lots of stuff, maybe too much sometimes, but I'll try to give you a brief overview of what we can use. So on the left-hand side, we have the workloads that we can launch on a Kubernetes cluster, which are usually deployments, which is the easiest one. So set of containers that contains my application and that runs in our infrastructure, or a daemon set, so containers that runs in every node that our cluster has, or jobs, containers that runs a bad job and then they shut down, which usually are Spark executors, for example. All of them maps to a replica set, which is the first Kubernetes API object that was introduced in Kubernetes, and it's the one that is responsible for managing the set of containers. This is not working. Okay. Hope you can hear me now. So replica sets was the first object that was introduced in Kubernetes since the first Borg version, the former name that Kubernetes has during the Google era. And it basically is responsible for managing the set of pods, which are the containers. So the pods is the lower level of what we can deploy in Kubernetes, and the replica sets is responsible for managing what we deployed. When we deploy a replica set, we set the number of replicas that we want. So it's very straightforward. It's a very simple API object, and I can set 2, 1, 3, depending on what I think I might need. Okay, let's do that. Okay, so all the pods lives a different life between the one and the other, so they're not connected to each other unless we want to, and is the replica set the manager of that. So what happens when we need to scale? So sometimes even for a web application, but of course for the Spark executor, it's very similar. But what happens when we need to scale up? So we can define some rules on or thresholds that we want to define when we want to scale up the number of pods that needs to serve our application. And in this case, Kubernetes provides us what we call the horizontal pod autoscaler, which is another container, again, that monitors the loads that the containers are receiving via the Kubernetes API, and also another object, which is the metric server that we won't discuss because it will be too much entropy for this purpose. So the horizontal pod autoscaler gets the metrics for the API and understands if we need to scale up the replica sets or not, scale up or down, depending on the amount of load that we are receiving. Okay, that's good. That's it. No, of course not. It's not it. So the horizontal pod autoscaler modifies the replica sets, and that's good. We have new pods that are new containers that are spinning up. But what happens if the nodes where these containers are running have no capacity? So we have not enough CPU, not enough RAM memory, to serve this pod. So the horizontal pod autoscaler keeps creating new container, but only a few of them move to a running state. The other ones remain in pending state, waiting for resources to be free. So pod remains in pending state. So the load that we are experimenting is not handled, and usually very bad things happen. So I will be very vulnerable, for example, on a DDoS attack, because I won't be able to serve the load, and in this case, my application will be shut down in a matter of seconds. So, okay, so that's just to say that Kubernetes is good, but not that good every time. So we need to have a full picture about it, because sometimes we can simplify things too much. So what we can do
we need vertical auto-scaling. So we need to scale up also the nodes. That's just the fancy name that we use to say that we need new capacity, new hardware capacity. And we have two ways of doing that. The first one is manual scaling. So I can simply powering on new nodes. If you are on an on-premise environment, I feel very sorry for you guys, but this will be the only choice that you have. And I feel very sorry also for all the other problems that you may encounter in on-premise environments, but that's the only choice that you have. But it also has some advantages, because I don't have to wait for a new node to spin up. When the horizontal pod autoscaler creates a new replica, this is immediately executed in the nodes where I have capacity. But it's also useful when I have a very predictable load. So even in cloud environments, if my load is very predictable, I can create a bunch of nodes, pre-create a bunch of nodes that are there, that are part of my cluster, and I know that I can serve that type of load. Of course, if my load is very different between time, so sometimes I have high peaks and for most of the time it's low peaks of loads. In that case, I might end up having lots of resources in an idle state, and this will cost me lots of money. The other solution is the cluster autoscaler, which is the project. I don't know if one commit can make me a committer, but I have one commit in the cluster autoscaler project. And this is CNCF project. That means that it's, first of all, it's part of the Kubernetes project itself, but being a CNCF project, it's just like Apache for Cloud Native Compute Foundation. So a guarantee of the quality of the project. And this project has one single aim: to provide a way to create new nodes on cloud environments. So AWS, Google Cloud, DigitalOcean, whatever, you name it. Lots of developers contributed to this project to provide this very useful plugin. If you are used to use Google Kubernetes engine, you will have it as default in your cluster. You don't even have to install it. It's provided by default by Google. Of course, the advantages of using this type of approach are very clear to everyone. So it's very cost effective. I power on a new node only when I need that. And I can power off nodes when I finish my job. So when the Spark job has completed this task. But there are also some cons. It works only for cloud environment, as I mentioned before, but also the provisioning time may be long. So depending on the cloud environment, but not just the cloud environment, even the region, the availability zone that you are, having a specific type of instance may take time. Our data scientists know it very well. When they need a GPU or a specific machine, they sometimes need to wait a couple of minutes. I'm not talking about hours, I'm talking about minutes, but you know, in an ETL job, it can be a very important span. So it really depends on your business needs. So you might also find a good trade-off between the two approaches that you can use. Maybe you can have a set of nodes that are prepaid and they're always there to serve the load, and then you can rely on the cluster autoscaler to have additional node only for very important peaks. I don't know, that's just an idea. So how everything changes, so how the picture that I showed you before changes. We have two new actors in that. So we have, of course, the Cloud API, because our autoscaler needs to interact with the Cloud API to request new nodes in whatever cloud provider we are using. And then we have the cluster autoscaler, that is a container written in Go, not in Python. I'm not if I'm safe to say it in this community. Why Go? Because it's a better language than Python for this type of thing. But this is just a container that contains the logic, that monitors the API from Kubernetes, understand whatever we need, a new node, depending on the state of the pods. So I have several pods in pending state that are not scheduled because I don't have enough resources. In that case, the cluster autoscaler realizes that something is not going wrong or is not going correctly, and try to understand which is the best node available for the cluster that can spin up to serve the request, and request the node to the API. Then it's up to the cloud provider to provide the machine, attach it to the cluster, and then serve the container in the pod. After that, everything is up again to the Kubernetes infrastructure. So it's not up to the cloud API. Again, we are using basic Kubernetes resources. Okay, so this is the approach that we choose for most of our services. And I'm speaking especially about the data science and data engineering clusters that are using this container. It's nothing proprietary. This is pure open source project that we use. And sometimes if you're a Kubernetes user, you don't even notice that the cluster autoscaler is there, but it's not guaranteed for every cluster. And we can set it up according to our needs, because every autoscaling group, so group of nodes, can be fine-tuned depending on on the use cases that it's serving. So if we have a use cases that requires at least a set of nodes always on, we can do that even if we have the autoscaler on. Next step for us, for the infrastructure team that I'm part of. So we're trying to integrate the work that the cluster autoscaler is providing us with the spot instances. So we want to optimize our cloud costs by using there is an article there that explains the tentative that we are going on right now. So to use this combination of cluster autoscaler and classic on-demand instances, so the one that we pay in full, with spot instances. Every cloud provider, in this case I'm talking about AWS, uses a set of signals that can alert the user that a spot instance is about to be terminated. And this message should be intercepted and used to reload the balance in order to not waste service time on your application. So we try to collect the event that one spot instance is going down via event bridge in this case, but again, we are experimenting on this. This message is sent to a queue, and then there is another container that is the brother of the cluster autoscaler that can receive these messages and decide whatever it needs to move everything from one autoscaling group to another. So let's say that I have one spot instances that is serving my database in this moment, or even a web application. And I receive this message. So my instance is about to be terminated. This container is capable of understanding if there is enough spot instance size in this region where the cluster is deployed to ask for a new spot instance and move everything before the instance is terminated, or if it has to fall back to the on-demand instances. This is what we're trying to achieve. Again, since we're using stateless application, both Spark Executor, Spark Jobs, data science training, or even web application, which are mostly stateless for how we design that, this can be a very important cost-saving activities that we can perform and that we're trying to go for. That said, I will leave the question for later, so I will leave the stage back to Luca. So, thank you.
Thanks, Luca. Okay. Checking again some few other advantages of using Spark on Kubernetes is the fact that you can have the Spark concatenates operator So basically, you can have this operator and describe the Spark applications with Kubernetes templates. So for example, if you have your code located somewhere, this is a Scala example, but you can do it with PySpark as well. And then you can use this kind of templates to fire up Spark jobs. And this is basically, this follows the attempt that was of the integration of Airflow Spark and the Kubernetes that I've mentioned before that has already been done by someone else. But one thing that we can appreciate of this Spark on K8s operator that has been released by Google is the fact that its performance basically is matching the one of Yarn. And in case you don't know, Yarn means yet another resource negotiator, and it is basically the resource negotiator of Cloudera and Hadoop clusters. So we can see that using Spark on Kubernetes doesn't mean that you are giving up some performance. Okay, here we are basically there with the performance. So this is also something that the industry usually thoughts when moving application or workloads on Kubernetes. So, of course, this is an example of using local SSD as drives. So this doesn't count the possible networking bottlenecks when using external services for data. And the fact that you don't have to deal, for example, with the example that we have mentioned, with Cloudera or EMR, it means that, for example, in the Cloudera example, that you don't have to sustain the high upfront costs. I haven't used Cloudera for the last couple of years, but I remember when I used it that there were a lot of upfront costs, and it was really hard to manage and to maintain. Specifically, that the documentation wasn't well enough to cover all of the steps to deploy a Cloudera cluster. These are the alternatives of hosting Spark on Kubernetes. And on the other hand, EMR, that is the Elastic MapReduce service of AWS. On the negative sides of this solution is the fact that it is not updated often, so that you don't have and you kind of have some kind of vendor lock-in when locking and when using EMR, the EMR service. Also, the fact that it is closed source, you don't know, for example, when you have some problem, if it is caused by your code, even if this is 99% of cases, or some AWS maintenance problem. And in some cases, it happened, and it's a wonderful thing to discover. Okay. Okay. Don't kill me. Okay. Okay, moving on, I'll go very briefly and short on that so that we can all start drinking again this stuff. About the integration of Airflow and Kubernetes, of course, we have all the advantages that we've mentioned before on the node autoscaling, but also the fact that I want to see some differences that there are between the Celery executor and the Kubernetes executor. So these are the two kind of executors that you can have when using Airflow. So on the Celery, basically, it is some sort of, how would I describe it? You can queue jobs on that and execute them in Python, okay? But the fact when you add that on top of Airflow, there is some sort of redundancy. Basically, it's like that if Celery does a part of on the same scope that also the Airflow is doing. So, and you also need some workers to be always on when using Celery, because on Kubernetes you can spawn pods only when you need them. But of course, when you have workers always on, you also have less latency. For example, if I had to do a DAG that has to do hundreds or thousands of tasks one after another, and they are just very small Python function, in that case, I'd say, okay, Celery as executor has an advantage. But for example, when the tasks take a bit more and you need a bit more of flexibility on the image, on the dependencies, or do you want to have the full control of the pod specification of those images and maybe use a sidecar pod for your tasks, in that case, the Kubernetes executor wins a lot. And on this case, on Server Executor, you also require some external services like RabbitMQ and Redis to use it. I must also mention that there is also a combination of these two, that is the Celery Kubernetes Executor or Kubernetes Celery Executor, I don't remember, in which you can use both and then queue jobs on different queues depending on what you want to use. But this is another story. Moving on, we can just see briefly how to use affinity, taints, and toleration with Airflow tasks. So the affinities, taints, and tolerations are some concepts on Kubernetes that basically say this kind of stuff. Specifically, node affinities can be used to bound some pods to a specific set of node. And you can do it with the preferred or with the required kind of version of node affinity to enforce or to prefer to locate some pods on some specific nodes. So for example, let's say that we need to use a GPU in a Kubernetes node, or you need to use a specific machine that has some specific networking feature because we want to have more performance on that. With this node affinity, we can bound these Airflow tasks into specific nodes. And with the taints and toleration, we can tell not to put any other pod on that on that node, but just the pods that we want on that. So I've just copied here a script that comes from the blueprints. That is another kind of service that AWS is using to ease the deployment of Kubernetes. So there is a spot dedicated node group in which we are using spot instances, and basically with this taint that says that these are spot instance and do not schedule anything. And we can use also this label to enforce pods on these nodes. And on the Spark executor pods, we are saying to have this toleration. So even if the key is we have a spot instance, we can still put pods into these nodes. And also we have this match expression that to prefer that these pods finish up into in nodes that have capacity type as spot. And these are just few examples on how we can describe this kind of interactions. Then I've just mentioned, because I don't want to bore you anymore, that we are using the Vault Secret backend for Airflow. So basically, we are using Airflow as we're using Vault, that is an external service developed by HashiCorp. They are the same that I've developed also Terraform. So it's a very strong company that focuses on these open source products, in which basically we can have our set of connections and variables into this external tool. And I think that that has been a good solution. I mean, because you can centralize the secret management of an entire team on top of that, so that you don't have to rely on Slack to share passwords specifically. Don't do that, or to rely on some external services like a secret manager from AWS. That for each password that you have to pay like 40 cents per month. That is. I mean, it's not a low cost to have. And that's it. I just mentioned some of the next steps without deep diving them too much. So one thing that you could also implement on this kind of architecture is pause pods. So as we mentioned before, when a pod is in impending state, basically you're going to trigger some sort of auto-scaling of your nodes in Kubernetes. But this means, what if you have some pods that are just there sleeping with a very low quality of service? So this means that they can be, overwritten or just destroyed by the Spark executor pods, for example. And so these pods have some sort of this usefulness. So basically, when you have these pods, you are anticipating the autoscaler need in a more way. So you basically have these pods sleeping, and that they trigger before your autoscaler. And another thing that you can have in this kind of architecture that you're still trying to figure out is how to optimize the sizing of the tasks. So how to optimize the pods and so on. Because of course, if you have 32 gigabytes nodes, you don't want to have a task that is using 17 gigabytes of RAM, because of course you can put two pods on the same node, and that would be a waste of resources. So this is also another method that we are exploring. Then to have a Spark history server centralized and centralized monitoring on Elasticsearch. These are all common features that we are currently working on. I mean, to centralize the monitoring of our Spark applications. And other things that we have that we didn't have time to mention is the fact that we can have so a lot of other decorators. Okay, we love decorators, guys. At least you know it. So basically, decorator strong. So basically, we have decorators, for example, to have a single AWS services. So, for example, you need, for example, to use SQS, SNS to send notification on some pods or something. So you have to create some some specific logic. You use this decorator, and you automatically have it as an argument of your Python function, and you can use that kind of decorator. Then another thing that is basically how to use a Spark Shuffle service, because this is something that is useful when you have scaling executors. Because when you have a number of executors that scale up and down, maybe this executor needs some data that, for example, is needed in some sort of in some next steps of the Spark lineage of action of transformation that needs to be done. But then you don't need their computing power, not even their RAM. So when having a software service, it is useful to store this data and to swap it between inside the execution of the Spark lineage. And also the fact to have a multi-user development environment in Airflow. And this is something that is really cool when you have to do it with the Airflow local executor, but not when you're using the Kubernetes executor, because unless you want to have everyone with their own local Kubernetes environment with Airflow deployed on that, is something that is not only achievable when not all of you have tower computers or some sort of that. There are other solutions, for example, to have dedicated namespaces in which we have a small Airflow deployment on that. And that's it. Key takeaways. So Spark on Kubernetes is production ready. Spark deployment with Airflow can be simplified and automated, and you can optimize resource allocation with Airflow and Kubernetes. Thank you, guys.
Questions?
Oh, okay.
May I hold it or? Okay, thanks. So, by the way, this is not, I'm a colleague of Lucas, and this is not a question to make you look good, by the way, so. All right, so you mentioned that, the auto-scaling capability of executor pods in Spark, right? And I was wondering, how does this tie in with the dynamic task allocation of Airflow? I'm talking about Airflow tasks here. Because I'm thinking, and as you showed earlier, the configuration that you provide to the task with Spark decorator must be known to Airflow at the DAG parsing step, right? Which is not runtime, it's before runtime.
This is true.
And I was wondering how if these two things can tie up with each other, if they do, and if in the future you foresee the possibility to do that.
Okay. I don't think that these two things collide with each other, because you are not trying to how to say to foresee the usage of this Spark dynamic executor allocation, because this will be done at runtime when the task will actually happen. That was something that you have to do. You have to know at, forgive me, compile time. So when you are trying to parse the DAGs and compile the Airflow DAGs, you have to know the minimum number of the Spark executor and the maximum number of Spark executor, and this is something that you have to set beforehand. After that, it is Spark. It is inside the Spark cluster that it can understand how to scale up and down your Spark executors.
Right. But
is there a way maybe from Airflow to give a hint to Spark on how many executors to spawn? So, okay, I'll repeat the question.
I know.
Is there maybe a way from Airflow to hint to give a hint to Spark on the number of
Okay,
executors?
this is some very sad news for us because it can be done in the Scala API of Spark, but not in the Python API. So maybe there is some Scala user there that is happy about to hear that. But I think that you can give hints about how to scale the Spark executors beforehand. Okay. Okay. Nice.
In post process.
Nice, nice. Any other question?
I have a curiosity in your company, how you integrate the work of data scientists in this architecture. I mean, we are data scientists, we have a procedure, a model, anything written in Python, obviously, and we want scale up, integrate in your system. You use a container, you rewrite some code.
Okay,
What
so
do you do?
there is some a specific part of the ML operations that are done on a separated system. On, for example, they can be done on Kubeflow, on other separated parts, for example, and use, for example, Argo flows. I think that, or something like that. But this is more focused on the data engineering part. So to prepare the data sources that then the data scientists can use in their own ML workflows. So it is how to prepare the starting point from then which they plug in and they start working on top of this. So I hope I have answered your question.
Maybe I can add something about how we deploy machine learning model in production and how we use that. So basically the output of the data pipelines that we run over Airflow or Spark is used then for training models. So we create that staging area of the data, and then we use more data scientist friendly tool like Kubeflow, for example, to I don't know, creating notebooks or even launching pipelines for training machine learning models. And here again, we're using the same basic infrastructure to get the GPUs, to get all the resources that we need. Usually in a different cluster, which is not the one for used for data engineering, but connected to in a sense that the data are shared between the two clusters. And then we deploy the model using a GitOps approach. So once the model is built, we have containers that wrap the models around it. We use Kserve for that, for creating API in Python that use the model and the framework with Kubeflow in this case. So relies on Kubeflow class on the Kubeflow stack to very easily, but how easily it is, I will leave the question for our data scientists because I don't know if they agree, but I think it's easy. To deploy the machine learning model into production in a very standard way. So you simply compile YAML file where you specify this is the image that I want to use, this is the model that I want to use, and then Argo will take care of syncing what you declared in your cluster, and then you will have the API. And again, new data comes, we start a new pipeline for training the model, and we upgrade the Argo template that will be used to deploy the model. Don't know if this answer.
Any more questions? No? Then last. Round of applause. So, if you want to join for the dinner,